Thank you very much. Thank you for having me. I'm a scientist. I'm an astrophysicist at MPE in Garching. And I'm not a historian of science. I'm not a librarian, even though I have some books for you. So I'm going to tell you a story, in fact, a first-hand account, and in some cases, second, third-hand account of a very long project that involved probably the largest scientific German-Russian collaboration, according to some sources, and as such has a lot of interesting facts in the history of the project I'm going to tell you about. Particularly, I'm going to tell you how happened that we put our precious scientific instrument on top of a rocket and launched it into space in July 2019. The difficulties in getting there, and also the difficulties that we face after launch. That's the outline of my presentation. I will give you first a brief history context of the eRosita and the Spectrum Röntgen Gamma mission. That's the full name of the German-Russian space mission. Mentioning some aspect of the German-Russian collaboration along the way. If time permits, I will intermezzo a little bit of what is the science that we do in a few minutes, and touch at the end on some open science issues that are probably more relevant or interesting for many of you. The history is long, as in many space science. Space science is expensive, and it takes a lot of luck and a lot of circumstances in order to be able to launch your scientific instruments into space. I'm not going to go through the entire history. You can find some references in the publication list in there. Of course, there is a history on the German side of the project and the history of the Russian side of the project. In these slides, I'm highlighting some key aspects of the German side of the project on the right-hand side, mainly to tell you how long it took from the idea, the conception of the experiment we wanted to do in the late 90s, following up a successful mission that our institute built together with US and UK scientists called ROSAT. Which performed the first survey of the entire sky in X-rays. Several new attempts was made to improve. I mean, once you have your data, you want to get more. That's typical what scientists want to do. Until in the early 2000s, a scientific opportunity opened up. There was the discovery of the dark energy and the accelerated expansion of the universe, and a geopolitical, if you want, opportunity came up in the willingness of the Russian Federation to revive its space science program, and a general sense that there was a lot of encouragement from both Europe and Russia to work together at the time. On the Russian side, the history is even longer. Rashid Srinyaev, a giant of the field, who was a scientist in Soviet Union, giving seminal contribution to cosmology and high energy astrophysics in the 70s and 80s, then moved to Germany to become director of the Max Planck Institute for Astrophysics in Garching. And he was already leading an instrument called Spectrum X Gamma in the late 80s. This was the first Soviet US-UK, a large Soviet US-UK international mission project that was almost realized. Many instruments were actually built in the late 80s, early 90s, but essentially the funding crisis of Russia and the Russian space program after the collapse of the Soviet Union killed this mission. And it was in the early 2000s, as I told you, that there was some more funding came up again in Russian Federation. And so first discussion with ESA to revive their mission, and then with Germany. And Peter Predel, the PI of the instrument in the early phases, managed to convince the German space agency DLR that it was worth investing in a bilateral mission. This is by all means extraordinary. Nowadays, if you want to do space science at this level in Europe, you go through the European Space Agency. Germany doesn't fund national or bilateral missions. Most of the space science budget goes through ESA. This was exceptional times, and in a sense, something that probably will never repeat again. But in 2009, the agreement was signed between the two space agencies, Roscosmos in Russia and DLR in Germany, to build this observatory. that would detect X-rays from celestial sources and map the entire sky with two instruments, eRosita, the biggest one, the most powerful one that we built at MPE, and the Russian instrument that works at slightly lower, different energies, a smaller mission that would have given Russia the ability to put themselves back in the map of space science called Artex-C. Original plan was to launch in few years with a Ukrainian rocket, Zenit Fregat. We ended up launching in 2019 with the Russian rocket, a more powerful one. The costs are estimated around almost 100 million euros on the German side. This was money almost half split between DLR and Max Planck Society. The costs on the Russian side are a bit harder to estimate, but they amount to maybe 1.5 times the cost on the German side. So these are not, these are huge costs, but for space science, this is a small/medium mission. It would probably cost almost twice if you do it with NASA or ESA because of the cost of the launcher and the industrial contractor. I mean, we did things that very few others could do, in the sense that the entire building of this sensitive instrument, the largest X-ray telescope ever built, was essentially done in one institute at MPE. Usually these are consortia that nowadays space science split their activities across different countries and different places. At MP, we had the scientific lead, the project management, we designed the instrument, we manufactured maybe 60–70% of the part. We did all the integration, the test, the data handling, processing, the archiving. Of course, with industrial partners and a few German universities to support our lab work. The work was proceeding more or less in parallel on the German and the Russian side in building these two instruments. Over the years, there are a lot of beautiful pictures you can look on the web of the instrumentation that we built. I'm not going to dwell too much on that. You can ask me later. These are the almost complete instrument in our lab at MP. It was fantastic to be able to see it grow in front of your eyes. This is the focal plane, so these are electronic CCD cameras like the one you have in your phone that are able to work in space to detect X-rays. And these are some of the final preparation in the testing facility near Munich. And if you talk about open science, we did something that I don't know how many have done. We put some of our flight hardware worth tens of millions of euros into tech, and we show it to the public. This was a few months before this was finally integrated, and we had a great time explaining to the public that what they were seeing would eventually go into orbit 1.5 million kilometers away from Earth. So clearly public engagement was top priority, at least on our side. Finally, the integrated instrument made its way to the cargo airport, to the cargo in the Munich airport in a very chill morning in January 2017. And we got snow on the other side in Moscow, and a dodgy-looking truck that, however, was able to deliver the precious instrument safely into the Russian lab. And then it really started. That was the time where all the components of the mission were coming together in Moscow. Several members of our team went back and forth to Russia, working together, solving problems for the following 2 years. And in the book I have here, we asked the member of our team to write down the recollection of their experiences, not just in dealing with Russian bureaucracy or with Russian engineers, also with German engineers, which is sometimes more complicated. But you know, all problems were solved. That's the real spacecraft in its integration hall before being sent to Baikonur, and this is just a couple of days before launch on top of the upper stage of the rocket. And this is the rocket approaching its launch pad, and that's after, of course, a few delayed and scrapped launches. People had to travel back and forth to Kazakhstan. Eventually, in July, the launch happened, and it was a perfect one. The new phase of the collaboration entered. Operations. There was a quite interesting setup in which The entire ground segment communicating with the spacecraft was in Russia, and we were over the phone for 2 hours a day, sending commands in order for them to be able to understand what our instrument was responding, because we only had the expertise to properly command eRosita. And we managed to do that through COVID. If you ask yourself, can you run a spacecraft 1.5 million from Earth from your home? The answer is yes, you can, if you have good internet connection. So we managed for 1.5 years to run the mission from home as well. So I'm going to pause here. I mentioned about this book. You will find interesting stories, anecdotes. In general, giving quite a good feeling that when you are when you're working together to a common goal, usually you are able to solve problems. And in fact, the collaboration at the working level, at least engineering technical level, I would say worked quite well. In fact, in the collection of memoirs, the common theme is breaking barriers, cultural barriers, mostly work culture. I mean, how many stamps do you have to put on my letter asking for permission to visit the site? Or what does it mean when they say no? Or what does it mean when we say no? And so on. Sometimes language barriers, procedural barriers, but you break it. And I think this is, every scientist that work across the boards with China or with other countries, that's what we do. We break barriers in order to get the science done. And yes, I forgot there is a nice video here, but this is the unpacking of eRosita once it reached the lab in Moscow. But I want to tell you a few things more, so I'm going to cut this video short and then take 2 or 3 minutes of your time to tell you what did we do with this instrument. Well, we did a map of the entire sky in X-rays. Just to orient yourself, these are the kind of coordinates of the map I'm going to show you. You're going to look at the entire sky in so-called galactic coordinates. So we are in the galaxy. We are looking through the Milky Way. The galactic center will be at the center of the image. And so the entire celestial sphere is projected onto this ellipse. It's a special projection that preserves areas. And so when we record the X-ray events on our camera, we can measure the energy accurately and their position in the sky. So you can, for example, look at how the entire sky look like at energies of about 0.3 to 0.6 kiloelectron volt. This corresponds to the temperature of millions of degrees, right? So millions of degrees is an interesting temperature because that's the temperature of the entire halo around the Milky Way. It's called virial temperature. So we are looking at gas in equilibrium with the gravity in the Milky Way with this particular map. But we are sensitive also to a bit higher energies. So here we are seeing a little bit hotter gas. And for example, we discovered for the first time, maybe you don't see it in this projection, but an hourglass-like figure of 8 centered on the center of the Milky Way, which are probably gigantic bubbles produced by an explosion at the center of the galaxy millions of years ago. There is a famous black hole at the center of the galaxy who may be responsible for this explosion. We don't know for sure. And we can even look at even hotter gas. At that point, at those temperatures, the Milky Way is almost completely transparent. There is no such hot gas in the Milky Way, so we are seeing the distant universe. On my screen is beautiful. You see a lot of little white dots. And these are very distant galaxies and black holes. And when you combine together, you have this fantastic map that, believe it or not, none of us in the team, we were too busy in trying to digest the data. None of us had thought about creating the right color scheme to generate the map until we had completed the scan of the sky after 6 months of operation. So after 6 months, we had very bright computer scientists in our team that look at only half of the sky. I'm going to tell you why in a second. And we were stunned. We were looking at the map that nobody had looked before. And then we immediately asked our Russian colleagues to do the same because, I mean, the world had to see the full sky, not just half of it. So in fact, this stays as the only full sky map that eRosita is generating in the public domain because of reason I will tell you in a second about data sharing or not. And here in this map, you can see many different objects, but this is not an astrophysics talk, so I'm not going to tell you about navigating through the X-ray sky, even though, of course, it's a very fascinating topic. But let me come in my last 10 minutes to topics that are a bit closer to the subject of this meeting. Well, there are three that I can thought about, and more of them we can discuss over dinner, over a beer, or tomorrow at breakfast. First one is the sky divided. The second one is data publication, return on investment, cultural differences in interpreting, as open as possible, as close as necessary. And then Russia invades Ukraine, and what happened to the project. So data sharing, yes, eRosita was built by our institute. However, of course, in the full picture of the mission, the cost of the launcher and the part that the German partner put together was estimated, or more or less having a value which was about half of the data that eRosita would produce. So I think it was clear that was at the outset, we are going to share our data half-half. How are we going to do it? And I wasn't there at the time, but in practice, we were told that this had to be approved by the Duma, and the Duma would understand something simple, and the simple thing to do was just to split the sky in two. And that, of course, doesn't mean that we are blind. The sky is shared for calibration of the instrument. We have the ability to look on both sides, as the Russians do, but we decided that we would only publish the data on our part of the sky, and they would only publish data on their part of the sky. Now, over the years, so we formalized this division very early on in 2011, and we formed the joint German-Russian committee to discuss matters of cooperation among each other and with international partners. This is a flagship mission. We are presenting data that would be useful for many other scientists throughout the world. How do we do it? This ended up being a bit more frustrating than the experience of the engineers. We made several attempts to establish collaborative processes, working groups, and we succeed in some, more on the technical side. To calibration working group, for example, has been working very well for a few years. But when it came down to science, where we were told that our team was too much bigger than their team, we would have outweighed their contributions. They needed some safe space to protect their young community. It's true that a lot of Russian scientists had left Russia, and so they needed, and maybe they saw this as an occasion to build up from the grassroots a community of scientists that would benefit from being, so to say, protected a little bit by not having to share their data with the world for a few years. Things turn out to be different, unfortunately. One peculiar aspect, which I think it's the extreme of how you can interpret as open as possible, as close as necessary, the actual detailed agreement signed by the two partners in 2009 have different, foresees already then, a different timescale for data publication. So while the German side is more following open science principle, so we have a little bit like we discussed about CERN, we have a 2 years timescale over which the data must be publicly released, not only the data, the software, the metadata. The Russian side didn't commit to do any data release. In fact, they would say we would decide after launch. And in fact, it's still the case today that if you go on, this is the MP site where you can access the data. These are available on ESA Sky, on NASA. You can see only half of the sky. Now, those are the data people can actually download and do science with, rather than just the image I've shown you. You see this divided sky. And in fact, at this point, while we released our first batch of data early last year, and as expected, we had a tremendous return in the sense of establishing worldwide collaborations, an impact in the literature, in the community in general. We still don't know if and when the other half of the sky will ever be released. Also because, of course, as you know, at some point, in February 2022, Russia invaded Ukraine, and very quickly, the pressure on us as the manager of eRosita, in fact, in running the operation was very, very strong, coming from within and without our team, eventually from the Minister of Research and the President of Max Planck Society and the director of our institute, that convinced us that the right thing to do at the time was to put eRosita in safe mode. This happened very quickly. In 4 days, we did it without pre-warning our Russian colleagues. This was quite a tense afternoon, but they were actually quite understanding. They did the set of operation that we asked them to do without objection, and eRosita was off. And it's been off since. In fact, we haven't been able to start scientific operations. Even though eRosita, by its nature, we cannot even observe the Earth, our instrument would break, and with X-rays, we are not able to do any spy satellite. This is purely scientific. In fact, it's recognized as non-dual use since the time we exported the instrument in Russia in 2017. There are some aspects in the sanction packages, EU sanction packages, that question the way we do this operation by communicating instruction, technical instruction via phone with Russia. I mean, it depends which lawyer you talk to, but it's clearly rather, of course, a legal worry, but also a big PR and matter of opportunity. So we have still ongoing support from DLR to work on our data. We still have planning more data releases, but only on the existing data. There is no plan for further science operation. And right now we are not working on the scientific side with our Russian colleagues. So I close with this beautiful image, but it's only half of the sky. Thank you.
Thank you very much for this very practical insight into your research experience. Are there questions for Andrea Merloni? Yes.
Maybe it works like this. Are you in the risk to lose your instrument? Or does it have to be recalibrated on the position in the sky, or what's happening? Because the Russians have to do it, right?
So, yes, I went a bit fast. I told you there are two instruments, so even after we switch off ours, they continued observing with theirs. So we know that the spacecraft is still safe, and we do get passively, so to speak, just received telemetry data that tell us that our instrument, even if it's in standby, so to speak, is still healthy. Of course, this was not designed to be off for so many years. You never know, but there shouldn't be too many risks in staying there for some more time.
Thank you. Further questions?
Thanks. Do you have any kind of lessons learned for, like I get the sense we would think ideologically it's a good idea to try and collaborate with people from contexts where there might be political risk, right? So it's maybe just because there's political risk isn't a reason to initiate a collaboration. But any lessons learned in terms of ways to avoid disruption, even if, let's say, governments end up, I mean, space is tough, right? But in the case of bio research or another field, any generalized lessons for this?
That's a bit tough. It's a lot to ask. I don't think I have that level of insight for many people. Of course, I mean, I wanted to convey a few things. This project takes a long time, and the situation at the beginning can be very different from what ended up being, right? Having said that, we experienced we had a positive experience of the collaboration. And in fact, the kind of science we do, of course, everything can be instrumentalized for propaganda, but it's almost as pure science as it gets. And in fact, there are existing other science cooperation. The International Space Station is the most prominent one in which things have not stopped. So a lot of people told us you should have reacted, you should have pushed back strongly. Of course, back then, nobody knew how long the war would have ended. And, at some point, this became, for the first time, while we had worked for 20 years, in a sense, a little bit under the radar, and despite this being a large, but we had a lot of freedom in the way of doing the way we wanted to do. This became all of a sudden very political, and I don't think we were ready, and maybe we didn't want to engage on that level. So having said that, if we were, we wouldn't definitely start a major program with Russia today, even though our institute is at forefront of China collaboration. We have major science, space science program ongoing with China, successful ones, in fact. And so, I think we are just trying to follow our science instincts. In fact, I am not the director. I'm not the one that takes the executive decision. So, but so far we are trying not to draw too many political lessons, rather go where the science leads us.
Thank you. Any further questions? Yes.
So you mentioned that the Russian side was interested because they were hoping to build up expertise. Obviously you said it is very much basic science, but of course it's tied to space expertise generally. When the times were different and you started this collaboration, what is your impression about the view of the German political side on it? Was it just kind of accepted as a byproduct that the Russian side would gain expertise, or was it actually seen as something positive?
Yeah, okay, I should qualify my statement a little bit. The whole reason why we entered in this collaboration in the first place was that on the technical level, Russian space industry still had expertise. They would still they would still be able to deliver competitive launcher at quality, right? So that expertise wasn't lost. The expertise that was lost was on the scientific side, right? And in fact, on that front, we had, of course, no problem if a community of astronomers based in Russia would develop more strongly. In the end, what it happened was that most of the leadership of this community to be were actually half based in Germany, and after the war, I think the funding on their side for working on eRosita data has gone almost down to zero. So not only their data are not public, but they are not even publishing their half very much. So in the sense, but of course, who would have predicted that in 2006?
Based on your experience, do you think that on the Russian side, there is some sort of dissemination of information system that evades our publication system, but they still have theirs somehow, and it's not accessible to us? Or I'm thinking very wild here, but what is your impression? It's very difficult to imagine that a country that has such strong scientists, of course, many of them migrate, disappears from the scientific literature. Is it disappeared, or is it transformed to something else that is more secret, not open?
Well, okay, of course, this I don't know. And in fact, I'm really telling you my impression for limited conversations that I have with colleagues. I think the situation right now is pretty catastrophic in the sense a lot of people have left since 2022, also scientists. Their system has closed in the sense that now they are, again, this is second-hand information, but a lot of, again, I'm talking about basic fundamental science here, not necessarily technology or applied research. Even in those cases, they are explicitly mentioning publishing in Russian journals as a way as important as in publishing Nature for their internal career. So they're kind of closing up their system. The young people are told if you publish on research note in Russian, a journal that maybe 1% of the readership of international journals, that's perfectly fine. You can still stay in the system. And of course, this makes them quite isolated, right? So my impression is that those who stay, I mean, they especially those in the institute we are working at is Russian Academy, is the Space Institute of Russian Academy of Science, which have a lot of prestigious international cooperation. All of them are dead, right? And so those that couldn't leave, didn't want to leave, I think they have accepted that their scientific standard must be different or lower than what it was 5 years ago. But again, maybe this is a bit partial in the sense that our particular community of high-energy astrophysicists were particularly affected. But from what I hear, my impression is a system that is closing up. I don't know what does it mean for the younger generation, but probably not much positive.
Thank you very much.
So I have few more, the one I could bring with me in my backpack. If you are interested in histories and anecdotes about our mission and collaboration with Russia, just come to me. I have a few copies of that. Thank you.
Thank you.